we're fortunate enough to have Victor Donnay with us, who's seen a lot of big pictures in his time at his tenure at Bryn Mawr. And he's going to tell us about bifurcation, or is he going to tell us about bifurcation? Has he decided which path he's going to take? So we'll wait and see. So Victor, you're on.
Great. Thank you so much, Brian. I'm so pleased to be here and getting to share one of my teaching approaches. So pretend this is your first day of the new semester. You're in my math class, and I always start off with this question: what are some problems facing the nation and the world that you are concerned about? Get in groups, make a list, report out, and for time's sake, imagine we've just done that. One of the answers, well, you can imagine there are many answers nowadays that people are concerned about. One is climate change, but there are many others too. So the goal of our course is to see how the mathematics we learn can connect to these problems that you're concerned about. And then often there are gasps from the students when they realize that we're going to try to actually connect our math to the real world and to what they care about. So that's my hook to get students interested and excited about mathematics. Quick question, maybe you can raise your hand in the side. How many of you include the topic of bifurcations in your differential equations class? Oh, great, I see some hands going up. Great, so in graduate school, I didn't actually learn about bifurcations much, and so it was through teaching that I learned about it. And so I'm gonna kind of talk about why I think it's such an important and interesting topic for us to share with our students. And partly it's because bifurcations in the common cultural world are called tipping points, and it's not often that a math idea gets a lot of currency in the general culture, and I think we should take advantage of that to show students that what we do in our math connects to stuff they might have heard about just in everyday life. This book, The Tipping Point by Malcolm Gladwell, talks about this issue. And as I mentioned, the students are often worried about climate change, the climate emergency, and you're reading the newspapers about tipping points in this climate system that could be really worrisome. If the temperature rises too much, the ice sheets, which are already melting, could eventually melt completely. And if we cross a certain temperature threshold, that may happen and become irreversible. Another big issue that one worries about is that all the permafrost in the northern climate, Siberia, northern Canada, could melt, releasing all the carbon that's been stored there. Or one I've recently learned about, if we burn down or cut down too many trees in the Amazon, there'll be a bifurcation where the forest will convert into grasslands. And then all the carbon that trees can store, we would lose that. The grasslands don't absorb as much. So here's a little mini assignment I like to give students. What are other tipping points in the Earth climate system? Find one, write a paragraph about it, post it on Moodle, read what the other students have come up with. And I think this is such an important idea because it's very counterintuitive. You would think that if you change your system a small amount, the end result would have a small impact on the system. But as the kids say, not. Bifurcations, you make a small change in the system if you're near one of these tipping points, and you'll have a very dramatic change. And that's a conceptual idea that our leaders and everyone should really understand as we face these climate issues and population dynamics, disease problems. That's an understanding that's really important to have, and traditionally one didn't really understand that. So first I'll give you a little video that I helped make about tipping points and climate at TED Ed, which was super fun to do, and connecting to my research in billiards and chaos theory.
For most of us, 2 degrees Celsius is a tiny difference in temperature, not even enough to make you crack a window. But scientists have warned that as CO2 levels in the atmosphere rise, an increase in the Earth's temperature by even this amount can lead to catastrophic effects all over the world. How can such a small, measurable change in one factor lead to massive and unpredictable changes in other factors? The answer lies in the concept of a mathematical tipping point. which we can understand through the familiar game of billiards. The basic rule of billiard motion is that a ball will go straight until it hits a wall, then bounce off at an angle equal to its incoming angle. For simplicity's sake, we'll assume that there is no friction, so balls can keep moving indefinitely. And to simplify the situation further, let's look at what happens with only one ball on a perfectly circular table. As the ball is struck and begins to move according to the rules, it follows a neat star-shaped pattern. If we start the ball at different locations or strike it at different angles, some details of the pattern change, but its overall form remains the same. With a few test runs and some basic mathematical modeling, we can even predict a ball's path before it starts moving, simply based on its starting conditions. But what would happen if we made a minor change in the table's shape by pulling it apart a bit and inserting two small straight edges along the top and bottom? We can see that as the ball bounces off the flat sides, it begins to move all over the table. The ball is still obeying the same rules of billiard motion, but the resulting movement no longer follows any recognizable pattern. With only a small change to the constraints under which the system operates, we have shifted the billiard motion from behaving in a stable and predictable fashion to fluctuating wildly, thus creating what mathematicians call chaotic motion. Inserting the straight edges into the table acts as a tipping point, switching the system's behavior from one type of behavior, regular, to another type of behavior, chaotic. So what implications does this simple example have for the much more complicated reality of the Earth's climate? We can think of the shape of the table as being analogous to the CO2 level and Earth's average temperature, constraints that impact the system's performance in the form of the ball's motion or the climate's behavior. During the past 10,000 years, the fairly constant CO2 atmospheric concentration of 270 parts per million kept the climate within a self-stabilizing pattern, fairly regular and hospitable to human life. But with CO2 levels now at 400 parts per million, and predicted to rise to between 500 and 800 parts per million over the coming century, we may reach a tipping point where even a small additional change in the global average temperature would have the same effect as changing the shape of the table, leading to a dangerous shift in the climate's behavior, with more extreme and intense weather events, less predictability, and most importantly, less hospitability to human life. The hypothetical models that mathematicians study in detail may not always look like actual situations, but they can provide a framework and a way of thinking that can be applied to help understand the more complex problems of the real world. In this case, understanding how slight changes in the constraints impacting a system can have massive impacts gives us a greater appreciation for predicting the dangers that we cannot immediately perceive with our own senses. Because once the results do become visible, it may already be too late.
So that was a lot of fun to make in partnership with the TED-Ed people, and it's been viewed about 180,000 times, so way more than any math paper I've ever been involved with. So that was kind of one introduction to this idea of tipping points, and now I'll outline how I get to it in my math class. And in particular, my goal is to show a teaching unit where the students get to discover the idea of bifurcations for themselves. So I learned this from the differential equations book by Blanchard, Devaney, and Hall that has a dynamical systems approach, which I like. So there's the exponential model of population that we know about, unlimited growth. That's slightly unrealistic. You can never have infinitely many people or a population. So we introduced the logistic model that has a carrying capacity of some maximum amount n. And high school students tend to have learned about carrying capacity in biology or environmental studies, so they're familiar with that notion when they get to our math classes. You can do change of variables and end up kind of assuming that your k and n are both 1, and 1 meaning you're kind of taking the ratio of your population over this carrying capacity. So here I'll just look at this particular case, but it can illustrate the different things that can happen. And basic technique, we have the slope fields of the differential equations, and then we get the curves. Some of them go up, some go down, depending on whether you're above or below the carrying capacity, which is here, that's 1. Negative values, which physically don't make sense, would go off to negative infinity. After we do the slope fields, one then learns about the phase line, which is kind of the projection of this motion onto one dimension. And we learn about equilibrium solutions that don't change. So 0 and 1 are both equilibrium solutions, and those become dots on the one-dimensional phase line. And then if you move downward, we give a down arrow on the phase line. These solutions going up get an up arrow, and these negative ones get a down arrow. And from this little diagram, you can quickly see that the up equilibrium point is attracting because nearby things move towards it, and the down at 0 equilibrium points repelling, solutions move away. What's a little harder for students to get the hang of is looking at this function f of p, which gives you the slope of these solution curves. So when you plot the slope field, you're using that function to get the slopes, but it's a little tricky for them to get the hang of what this function is telling you. When the function is 0, that's where the slope is 0, and those are the equilibrium solutions. When the function's positive, that means the slope is positive, and solutions will go upward. And negative f means negative slope, and you're going down. But they get mixed up with the slope of the f function rather than the f itself representing the slope. So then we expand the model and add a harvesting term to the logistic, this negative c, which is the amount of harvesting done in the year. This could represent the fish caught in a fishing scenario, or it could be the trees harvested per year. And there's interesting stuff about sustainable forestry and what kind of sea level could you have there. But I tend to focus more on the fish, and we have all kinds of real world situations of what's going on in fish systems. So questions you could ask: how does changing the fishing level impact the population? And if we want to maximize our profit, what fishing level should we have to do that? And that leads to the bifurcation diagram. I don't show it to them, but I'll show it to you. This is where we're going to end up with our student project, which is kind of a complicated object. Each of these lines is itself a phase line. You have many different phase lines. You have all these equilibrium points. So it's a lot for students to digest. And my goal is to have a hands-on exercise, which helps them kind of create and discover it for themselves. So it's a group cooperative learning project. It's called the jigsaw approach. So I'll divide students into groups of usually 4 students. And each student in the group gets 2 different C values. So again, our idea is we want to look at different C values. What do the phase lines look like? And then we're going to put all these C values together to make this bifurcation diagram. Once a student has been assigned their 2 problems, and actually I can give you a quick look at the handout I give. So put them in a group. They sign their name, and that determines their 2 C values. So then they go off, and all the people with the same C values, like all the people number 2, get together and figure out their 2 phase lines so that they don't have to do it by themselves. They get to talk about it with their classmates and help each other. And then we return. So I can do this within 1 class period. I tend to have 65, 70-minute classes so that I can do group work. So then they come back and they share their results with their teammates. And so what they have to do for each C value, first they have to draw this slope function. Maybe we use technology for that. In one of the earlier talks, I saw Desmos, which would be a nice way to do it. Determine the equilibrium points, draw the phase line, indicate whether the equilibrium point is attracting or repelling through these arrows. And so here we'll do a little interactive work. I don't want to give a lecture about group work and just lecture on it, but it's a little tricky to figure out how to do an interactive thing on Zoom. So you have these 3 values. We've already drawn the F function, and now maybe on a piece of paper, figure out what your phase lines would be like for each of these 3. Recall that once we have the function, the zeros of the function are the equilibrium points. And then positive function means the slope is up. So there you draw up arrow. Negative function means a negative slope. So I'll give you a minute to work on that, and then we'll come back together and see what we got. Maybe you can raise your hand on the board if once you're finished, get a sense of how folks are doing. Again, a little reminder, once you have the function, any zeros will be the equilibrium points. Negative values of the function, the arrow goes down. Positive, it goes up. All right, 30 seconds more, and then we'll see what we've come up with. Well, great, I see some hands raised. I appreciate people both putting your hands up and also having some of your screens open. So it's not like talking to a blank wall. Okay, so let's see what we got. Little self-test. You can see maybe before you even do that, grade yourself. Do you feel like you have mastery of this new concept? Maybe you're developing your knowledge, or maybe you're in the not yet category. So when C was 0, we already drew this one with the 2 equilibrium and the up down. At 0.15, they're 2 equilibrium, but they're closer together. And first, for small values, it's down, positive, and then negative. This second one is interesting. There's only 1 equilibrium point, and on both sides of it, the function's negative, so the phase line goes down. And then this one, there are no equilibrium points. It's always negative. So things are just going down. If you finished it, is that what you got, folks? See some heads nodding, great. So we only did a couple, but the students have a few more C values. They have 8 in all in their group when they put it all together. So they get this kind of picture. And then I say, well, connect the dots. So they kind of fill in the ones in between. And maybe I say, use one color when you connect the dots that are attracting and a different color when it's repelling. And then I give them in the worksheet some questions. What happens to the fish population long-term if there's a high fishing level? And what happens if there's a low to moderate? I don't say what high is, but if we're over here, they'll realize that the fish population just keeps going down. Would actually go to negative infinity, but physically, that means the fishing will get extinct at some point. Low level, there's a range where if you have a lot of fish, you'll decrease, but less you'll increase, and you'll come to this attracting equilibrium so that you'd have a steady state amount of fish that would stay there in the long term. So you'll be able to keep fishing forever. So in Victoria's talk, she talked about having kind of a case study where you report out to some company. So I have a little bit like that too. The Government Department of Fisheries has set up a fisheries commission. They want to come up with a quota for how many fish can be caught each year. And now you, as an expert on the mathematics of fish population, are being called to testify before the Fisheries Commission. Based on your mathematical analysis, what recommendation will you give to the commission? So in their groups, they have to kind of write out, and if they've figured out that this value right here is the dangerous one, they hopefully will say, well, we shouldn't fish beyond 0.25, or maybe we shouldn't even go quite that much. So they have a little fun about using their math in a real world situation. And this type of thing, I live in Philadelphia. New Jersey had a robust fishing industry that's gotten overfished. The East Coast, in Canada, where I grew up partly, this is a real world issue of overfishing and crashing the fish population. So then we ask, what is this critical fishing level below which the fish population will survive and above which it will die out? And this is called the tipping point, or in mathematics, the bifurcation point. And they see that that's at the C equal 0.25 in this choice of coordinates. So they've been guided in a structured way to discover for themselves the bifurcation diagram and to discover this idea of the tipping point. And so kind of the summary here, we see that the tiniest bit below 0.25, you can have a steady state fishing population. You can run your fishing company and have a robust fish harvest every year. But the minute you go the smallest bit above that, you'll crash the population. So that's this very counterintuitive notion of a small change in our system, the C value, leading to a dramatic, and in this case, really unfortunate change in behavior.
So Victor, we have about 5 minutes in our allotted time. Okay,
great.
Doing fine.
I had the chance to be the coordinator of Math Awareness Month in 2013. It was the mathematics of sustainability. And we got about 15 essays by different people about how math got used in their field. So there's some on environmental issues. So that might be something your students would enjoy going to and reading about. And there's short little essays about these different posters. But one of them here, you see a fish situation, is a discussion about this over harvesting of fish and how mathematics can model that. I'm a Philadelphia sports fan. You may know the Eagles played at the Super Bowl on Sunday. And so my top win in this Math Awareness Month was getting an essay from the Philadelphia Phillies baseball team on how they're a green operation and use math to kind of analyze their recycling, waste management, and energy usage. So here I'll finish. I've been teaching at Bryn Mawr College for 32 years, since 1990. It's been a great time. Our logo, or at least my logo as a math teacher, is do the math, feel the power. That in today's world, knowing math and being able to use math opens a lot of doors. And we've had a great program with a lot of students being math majors, and we were fortunate enough to win the American Mathematics Society Exemplary Math Award, Math Department Award for these efforts. Here are some references, a few of the tipping points, and the presentation came from an article I wrote for the UMapp Journal on discovering bifurcations. And I want to thank Paul Campbell, who encouraged me to write the article and did a lot of great editing to put it in good shape. So that's it. I'm going to give another talk on Sunday about teaching with math and sustainability and having community-based projects for my students. So it'd be great to have you come meet, hear about that work too. So thanks, this was fun.
Thank you very much, Victor. Any comments, questions about the kind of the elegance and the ability to ask students to look at pictures and say things, experiences you, others? Yeah.
It's a wonderful presentation.
Thank you.
Can I ask you, I found that the most difficult part for students is to find the shape, this parabolic shape of the line where the behavior changes, right? How do you teach, how do they find this?
So in this exercise, I make sure to give at least one of the groups of students the exact C value where you have the one equilibrium point. A more interesting example, or a version, you could give this worksheet, but let them pick some of their own C values, and then they may or may not do it. But I talk of a bifurcation as when the phase line changes. So if before they're 2 and after then the key one is 1, and so they kind of look at that in their equation. But graphically, sometimes we do an animation where as C changes, you see that the parabola moves. And so you're looking for the point where it shifts from having the equilibrium points to not having it. So kind of different ways. I like the visual way, and maybe that animation and the way you change it. And for calculus even, we want them to recognize patterns, and we don't want them to always have to like plot every point in a graph. So if we teach them that you have x squared and then plus c minus c is moving it up and down, that reinforces, I think, a useful way of thinking about graphs.
If I can make a comment, because tomorrow I'm giving a talk at 5:30, which is almost like part 2 of this talk. So we're developing a little more complicated population model, and we're considering the constant effort harvesting, where you're not harvesting a constant amount, but a constant proportion each time period, which is in some sense more realistic. And again, you get with certain species, you get bifurcation, the saddle node bifurcation, very similar to what you had here. Except the problem here, you had the, once you pass the bifurcation point, you go to minus infinity. And in these models, once you pass the bifurcation point, your solutions actually do go to zero.
Ah, nice.
So
Great.
I
hate
actually
to
had in
plug myself.
mind the shape of the parabola that determines the position of the stationary point with respect to the parameter. So I had in mind this shape, and I mean, the shape of the bifurcation graph depends, of course, on the model. So my students find this a bit challenging to find the shape of this bifurcation graph. This parabolic dependence of stationary point on the parameter.
The kind of finale of the project, which I didn't mention here, is to do these calculations for a general value of the parameter rather than a specific number, and then try to graph that.
Going to ask us to, since both Jim and Victor are going to be on again, we can have further discussions. We're going to start our next talk in this room at 8 o'clock. But I just wanted to point out that when I was studying differential equations in the early 1960s, we just ground out solution after solution. The idea of qualitative behavior and analyzing and bifurcations and all this kind of stuff was not in any of my instructors' purviews. And it makes the differential equation study much richer, much more exciting. And I just can't tell you how it excites me to know that this is what's happening in this field. And I'm glad we're talking to some leaders in that regard. Well, thank you again, Victor.